Today I will talk about linear discriminant analysis. It is part of my series of lectures on machine learning. This is my lecture outline. First I will give an introduction, then I'll talk about geometry of LDA, then I'll talk about mathematical basis of Fisher's LDA and generalized LDA, then I'll talk about variants of LDA, then I'll talk about assumptions of LDA, then I'll talk about similarities with other algorithms. Then I'll talk about applications of LDA, and finally I will give an example with Python code of linear discriminant analysis. So linear discriminant analysis is a supervised machine learning algorithm. It is used for categorical dependent variables. It is a linear model. It is a dimensionality reduction algorithm. It is a feature extraction method and not feature selection method. It was first described by Fisher in 1936 for binary outcome variable, and it was later extended by Rao in 1948. So linear discriminant analysis in terms of geometry. Let us say a data contain three variables, a variable y, which is an outcome variable with two classes. Here, one class is on red, the other class is on blue, and there are two independent variables, x1 and x2. So if we consider a particular variable as a discriminant for these two classes. So this is the projection of the data points on x1 variable. So there is lot of overlap and mix-ups. So the variable x1 alone cannot be used to differentiate between the classes. However, if we take a rotated line in such a way that we can differentiate the two classes very well. This is what we do in linear discriminant analysis. So we have found a single dimension, a single line, a single variable, which is a reduced dimension of two variables on which we can project the data points and we can differentiate the two classes of data points. So this is what is known as linear discriminant analysis and mathematical basis of linear discriminant analysis. So first I will talk about Fisher's linear discriminant analysis. Fisher's defined for two groups. So linear discriminant analysis maximizes difference between groups and minimizes scatter within groups. So for two groups, we maximize Fisher's index, that is AW, which is given as in numerator there is difference between means squared divided by this term, which is the scatter. Then let vector W is the direction of projection of our LDA line, which I have described in geometry. Then projection of sample is transpose of W multiplied by the matrix of independent variables. Then projection of mean is transpose of W multiplied by mean of the independent variables. Then variance of a particular group is given by this scatter, which was in denominator. So scatter of a particular group J is defined as this. By replacing the mean with this term here, we get this. Then by simple rearrangements, we get scatter as the group number multiplied by transpose of vector W multiplied by variance of group J multiplied by vector W. Hence the numerator became W transpose multiplied by scatter between multiplied by W, and denominator becomes W transpose scatter within multiplied by W. Thus, the Fisher's index is given as this divided by this. So for maximization, we calculate the derivative of Fisher's index with respect to W and set it to 0. So we calculate the derivative and set it to 0. So if this entity is 0, then this numerator should be 0. So rearranging this again becomes this. So this is a classic generalized eigenvalue eigenvector problem where A corresponds to scatter between, B corresponds to scatter within, and lambda corresponds to Fisher's index. So we can solve this using solution of eigenvalue eigenvector problem. Then generalization of the linear discriminant analysis for more than two classes. So this is the Bayes theorem for probability of AI, so that B has already happened is given by this. It is the probability of AI multiplied by probability of B so that A has happened divided by summation of this numerator term for all the other groups. Whereas Gaussian distribution, as we know, is given by this equation, this formula. Then the group assignment is probability of a particular group subject to our data, input data. These are the independent variables. This is given by this according to this Bayesian theorem. If it is more than probability of group J subject to our data. So if this is more than this, then the numerator should be more than this because denominator is same. So we get this inequality. In metric notation, the normal distribution is given by this. So using the logarithmic function, we finally get probability of group I and probability of group J. So this is used for classification of a particular case to a particular group. Then types of linear discriminant analysis. These are variants. So one is quadratic discriminant analysis. Second is flexible discriminant analysis. And third is regularized discriminant analysis. Then assumptions. These are the assumptions for linear discriminant analysis. Observations should be independent of each other. This is same as that of logistic regression. Distribution of each variable should be normal because we have used Gaussian function in our derivation. And covariance should be identical across different classes. There should be no outliers, and prediction power can fall if the correlation between variables are high. Then similarities with other algorithms. So similarity with principal component analysis. Principal component analysis like linear discriminant analysis works for numerical data. So both of these are for numerical data. Principal component analysis maximize variance, whereas linear discriminant analysis maximize separability of groups. Principal component analysis arranged in order of explained variance. So the components are arranged in order of explained variance, whereas the linear discriminators are arranged in order of separability. PCA is unsupervised, where LDA is supervised because we already have classified data. Number of components is either number of variables or number of samples, whichever is lower. Here, number of factors is either number of variables or number of classes of dependent variable, whichever is lower. So similarity with logistic regression, both are linear techniques. In both, outcome variable is categorical. Logistic regression is usually limited to two class problem, although there is multinomial logistic regression available, whereas LDA is for more than or equal to two classes. Logistic regression is unstable with well separated classes, whereas LDA is not. Logistic regression is unstable with small sample size, whereas LDA is not. Similarity with ANOVA, both are linear combinations of features. In ANOVA, there are categorical independent variables, whereas in LDA, there are continuous independent variables. In ANOVA, there is a continuous dependent variable, whereas in LDA, there is a categorical dependent variable. So these are the similarities and differences between ANOVA and LDA. Then applications of LDA. So these are the historical applications of LDA. One of the application is bankruptcy prediction based on accounting ratios and other financial variables. The other application, historical application, is face recognition. Then other applications, potential applications are to differentiate various types of customers, to differentiate various types of products for product positioning. And there are many applications in biomedical research. Then Python code. First of all, we import the useful libraries. This include the pandas for data frame, numpy for array and mathematical calculations, then pre-processing for standard scalar, then model selection for test train split, and discriminant analysis for linear discriminant analysis. Then these are libraries for graph plotting. So this is our data. I will use wine data in this example. So first of all, we split the data in test and train set. Then we scale our data. So these are the scaled independent variables. So dependent variable is categorical. So we leave it as it is. Then this is to see the explained variance. So this code is to see explained variance. So first of the uh, linear discriminant explains 68% of variance, whereas both of the components explain 100% variance, and the second component contribute 31% of the explained variance. So this is the linear discriminant analysis coding for fitting and transformation. So it transforms the independent variables to reduced dimension variables. So these are reduced dimensioned variables. Our X train and X test are reduced in dimension. Reduced form in 2 dimensions can be used for training of other algorithms like the decision tree or support vector machine, etc. This is the plot of the first and second component. So there is a good separability of the trained uh, reduced dimension. This is the same for test data. The reduced components, first 2 components, they are very well separating the classes. Then these are some useful outputs which include y prediction of the class. Then these are predicted probabilities. Then these are the scalings. And this is the printout of scalings. The number of rows is equal to the number of independent variables. And these are first 2 components or factors or linear discriminants. So this is the plot between the y predict and y test. This is the prediction, this is the actual. So there are 3 groups, group 1, group 2, group 3, and this is the misclassified dot. So this is all for today. Thank you very much.